Hello, good day everyone. Welcome to another session in astronomy. If you look at the sky, when you are far away from the city lights, there seem to be an overwhelming number of stars up there. In reality, only about 9,000 stars are visible with the unaided eye from both hemispheres of the planet. The light from most stars is so weak that by the time it reaches Earth, it cannot be detected by the human eye. So how can we learn about the vast majority of objects in the universe that our unaided eyes simply cannot see? In this chapter, we describe the tools astronomers use to extend their vision into space. In the 20th century, our exploration of space made it possible to detect electromagnetic radiation at all wavelengths, from gamma rays to radio waves. The different wavelengths carry different kinds of information, and the appearance of any given object often depends on the wavelength at which the observations are made. Let's discuss telescopes. This serves as a bucket for collecting visible light or radiation at other wavelengths, as shown in this figure. This shows the Orion region at different wavelengths. The same part of the sky looks different when observed with instruments that are sensitive to different bands of the spectrum. Visible light in Figure A shows part of the Orion region as seen by the unaided eye, with dotted lines added to show the figure of the mythical hunter Orion. Figure B shows X-rays. The view emphasizes the point-like X-ray sources nearby. The colors are artificial, changing from yellow to white to blue with increasing energy of the X-rays. The bright, hot stars in Orion are still seen in this image, but so are many other objects located at very different distances, including other stars, star corpses, and galaxies at the edge of the observable universe. In Figure C, infrared radiation, we mainly see the glowing dust in this region, just as you can catch more rain with a garbage can with a coffee cup. Large telescopes gather much more light than your eye can. Second, there is an instrument attached to the telescope that sorts the incoming radiation by wavelength. Sometimes the sorting is fairly crude. For example, we might simply want to separate blue light from red light so that we can determine the temperature of a star, but at other times we want to see individual spectral lines to determine what an object is made of, or to measure its speed. Third, we need some type of detector, a device that senses the radiation in the wavelength regions we choose and permanently record the observations. The history of the development of astronomical telescopes is about how new technologies have been applied to improve the efficiency of these three basic components: the telescopes, the wavelength sorting device, and the detectors. Now let's first look at the development of the telescope. The most important functions of a telescope are: 1. To collect the faint light from an astronomical source, and 2. To focus all the light into a point or an image. Most objects of interest to astronomers are extremely faint. The more light we can collect, the better we can study such objects. And remember, even though we are focusing on visible light, first, there are many telescopes that collect other kinds of electromagnetic radiation. Let's calculate the light collecting area of a telescope. The question is, what is the area of a 1-meter diameter telescope, a 4-meter diameter one? The solution: using the equation for the area of a circle, we have area is equal to pi diameter squared over 4. The area of a 1-meter telescope is pi times 1 meter squared over 4 is equal to 0.79 meters squared. The area of a 4-meter telescope is 12.6 meters squared. Most telescopes have mirrors or lenses, so we can compare their light gathering power by comparing the apertures or diameters of the opening through which light travels or reflects. The amount of light a telescope can collect increases with the size of the aperture. A telescope with a mirror that is 4 meters in diameter can collect 16 times as much light as a telescope that is 1 meter in diameter. The diameter is squared because the area of a circle equals pi times diameter squared over 4, where diameter, or d, is the diameter of the circle. Show that the ratio of the two areas is 16:1. Remember, 12.6 meters square is the area for 4 meter diameter telescope and 0.79 meters square for the 1 meter diameter telescope. Divide these two, you have 16. Therefore, with 16 times the area, a 4 meter telescope collects 16 times the light of a 1 meter telescope. Let's talk about formation of an image by a lens or a mirror. Whether or not you wear glasses, you see the world through lenses. They are key elements of your eyes. A lens is a transparent piece of material that bends the rays of light passing through it. If the light rays are parallel as they enter, the lens brings them together in one place to form an image. If the curvatures of the lens surfaces are just right, all parallel rays of light, say from a star, are bent or refracted in such a way that they converge toward a point called the focus of the lens. At the focus, an image of the light source appears. In the case of parallel light rays, the distance from the lens to the location where the light rays focus or image behind the lens is called the focal length. Since Newton's time, when the sizes of the mirrors in telescopes were measured in inches, reflecting telescopes have grown even larger. In 1948, U.S. astronomers built a telescope with a 5-meter diameter mirror on Palomar Mountain in Southern California. It remained the largest visible light telescope in the world for several decades. The giants of today, however, have primary mirrors, the largest mirrors in the telescope, that are 8 to 10 meters in diameter, and larger ones are being built. So that figure shows one of the giant, or the largest visible light telescope in the world. Modern visible light and infrared telescopes. Technological advancements had finally made it possible to build telescopes significantly larger than the 5-meter telescope at Palomar at a reasonable cost. New technologies have also been designed to work well in the infrared and not just visible wavelengths. The differences between the Palomar telescope and the modern Gemini North telescope are easily seen in the figure. The Palomar telescope is a massive steel structure designed to hold the 14.5-ton primary mirror with a 5-meter diameter. Glass tends to sag under its own weight, hence a huge steel structure is needed to hold the mirror. A mirror 8 meters in diameter, the size of the Gemini North telescope, if it were built using the same technology as the Palomar telescope, would have to weigh at least 8 times as much and would require an enormous steel structure to support it. The 8-meter Gemini North telescope looks like a featherweight by contrast, and indeed it is. The mirror is only about 8 inches thick and weighs 24.5 tons, less than twice as much as the Palomar mirror. The Gemini North telescope was completed about 50 years after the Palomar telescope. Engineers took advantage of new technologies to build a telescope that is much lighter in weight relative to the size of the primary mirror. Voyagers in astronomy. George Ellery Hale was a giant among early telescope builders. Not once, but 4 times, he initiated projects that led to the construction of what was the world's largest telescope at the time. And he was a master at winning over wealthy benefactors to underwrite the construction of these new instruments. Hale's training and early research were in solar physics. In 1892, at age 24, he was named Associate Professor of Astrophysics and Director of the Astronomical Observatory at the University of Chicago. At the time, the largest telescope in the world was a 36-inch refractor at the Lick Observatory near San Jose, California, taking advantage of an existing glass blank for a 40-inch telescope. Hale set out to raise money for a larger telescope than the one at Lick. One prospective donor was Charles T. Yerkes, who, among other things, ran the trolley system in Chicago. The performance of a telescope is determined not only by the size of its mirror, but also by its location. Here we will discuss the factors in picking the best observing sites. Earth's atmosphere, so vital to life, presents challenges for the observational astronomer. In at least 4 ways, our air imposes limitations on the usefulness of telescopes. 1. Weather conditions. 2. Dry sites, generally found at high altitudes. 3. The sky above the telescope should be dark. And 4. The air is often unsteady. The best observatory sites are therefore high, dark, and dry. The world's largest telescopes are found in such remote mountain locations as the Andes Mountains of Chile, the desert peaks of Arizona, the Canary Islands in the Atlantic Ocean, and the Mauna Kea in Hawaii, a dormant volcano with an altitude of 13,700 feet. Astronomers are always eager to make out more detail in the images they study, whether they are following the weather on Jupiter or trying to peer into the violent heart of a cannibal galaxy that recently ate its neighbor for lunch. One factor that determines how good the resolution will be the size of the telescope. Now let's talk about the resolution of a telescope. This refers to the precision of detail present in an image, that is, the smallest features that can be distinguished. Larger apertures produce sharper images. Until very recently, however, visible light and infrared telescopes on Earth's surface could not produce images as sharp as the theory of light said they should. The problem is our planet's atmosphere, which is turbulent. It contains many small-scale blobs or cells of gas that range in from size inches to several feet. Each cell has slightly different temperature from its neighbor, and each cell acts like a lens, bending the path of the light by a small amount. This bending slightly changes the position where each light ray finally reaches a detector in a telescope. The cells of air are in motion, constantly being blown through the light path of the telescope by winds, often in different directions at different altitudes. As a result, the path followed by the light is constantly changing. The resolution of an image is measured in units of angle on the sky, typically in units of arcseconds. 1 arcsecond is 1/3600 degree, and there are 360 degrees in a full circle, so we are talking about tiny angles on the sky. But since we can't put every telescope into space, astronomers have devised a technique called adaptive optics that can beat Earth's atmosphere at its own game of blurring. This technique, which is most effective in the infrared region of the spectrum with our current technology, makes use of a small flexible mirror placed in the beam of a telescope. A sensor measures how much the atmosphere has distorted the image, and as often as 500 times per second, it sends instructions to the flexible mirror on how to change shape in order to compensate for distortions produced by the atmosphere. The light is thus brought back to an almost perfectly sharp focus at the detector. This figure shows just how effective this technique is. With adaptive optics, ground-based telescopes can achieve resolutions of 0.1 arcsecond or a little better in the infrared red region of the spectrum. This impressive figure is the equivalent of the resolution that the Hubble Space Telescope achieves in the visible light region of the spectrum. After a telescope collects radiation from an astronomical source, the radiation must be detected and measured. The first detector used for astronomical observations was the human eye, but it suffers from being connected to an imperfect recording and retrieving device, the human brain. Photography and modern electronic detectors have eliminated the quirks of human memory by making a permanent record of the information from the cosmos. The eye also suffers from having a very short integration time. It takes only a fraction of a second to add light energy together before sending the image to the brain. One important advantage of modern detectors is that the light from astronomical objects can be collected by the detector over a longer period of time. This technique is called taking a long exposure. Exposures of several hours are required to detect very faint objects in the cosmos. The photographic and electronic detectors. The instrument between telescope and detector may be one of several devices that spread the light out into its full rainbow of colors, so that astronomers can measure individual lines in the spectrum. Such an instrument is called a spectrometer, because it allows astronomers to measure or to meter the spectrum of a source of radiation. Whether a filter or a spectrometer, both types of wavelength sorting instruments still have to use detectors to record and measure the properties of light. Astronomers today have much more efficient electronic detectors to record astronomical images. Most often, these are charge-coupled devices or CCDs, which are similar to the detectors used in video camcorders or in digital cameras. In a CCD, photons of radiation hitting any part of the detector generate a stream of charged particles or electrons that are stored and counted at the end of the exposure. Each place where the radiation is counted is called a pixel or picture element, and modern detectors can count the photons in millions of pixels or megapixels. Because CCDs typically record as much as 60 to 70% of all the photons that strike them, and the best silicon and infrared CCDs exceed 90% sensitivity, we can detect much fainter objects. Among these are many small moons around the outer planets, icy dwarf planets beyond Pluto, and dwarf galaxies of stars. CCDs also provide more accurate measurements of the brightness of astronomical objects than photography, and their output is digital, in the form of numbers that can code directly into a computer for analysis. This figure shows the CCD, which is a mere 300 micrometers thick, thinner than a human hair, yet holds more than 21 million pixels, and this matrix of 42 CCDs serves the Kepler telescope. Spectroscopy. It is one of the astronomers' most powerful tools, providing information about the composition, temperature, motion, and other characteristics of celestial objects. More than half of the time spent in most large telescopes is used for spectroscopy. The many different wavelengths present in light can be separated by passing them through a spectrometer to form a spectrum. The design of a simple spectrometer is illustrated. Light from the source, actually the image of a source produced by the telescope, enters the instrument through a small hole or narrow slit and is collimated in the collimating lens, made into a beam of parallel rays by a lens. The light then passes through a prism, producing a spectrum. Different wavelengths leave the prism in different directions because each wavelength is spent by a different amount when it enters and leaves the prism. A second lens, placed behind the prism, focuses on many different images of the slit or entrance hole into a CCD or other detecting device. This collection of images spread out by color is the spectrum that astronomers can then analyze at a later point. As spectroscopy spreads the light out into more and more collecting beams, fewer photons go into each beam, so either a larger telescope is needed or by the integration time must be greatly increased, usually both. There are also certain observations made outside the Earth's atmosphere. Infrared observations from airplanes have been made since the 1960s, starting with a 15-centimeter telescope on board a Learjet from 1974 through 1995. The NASA-operated a 0.9-meter airborne telescope flying regularly out of the Ames Research Center south of San Francisco, observing from an altitude of 12 kilometers. The telescope was above 99% of the atmospheric water vapor. More recently, NASA, in partnership with the German Aerospace Center, has constructed a much larger 2.5-meter telescope called the Stratospheric Observatory for Infrared Astronomy, or SOFIA, which flies in a modified Boeing 747SP. The most powerful of these infrared telescopes is the 0.85 meter Spitzer Space Telescope, which launched in 2003. A few of its observations are shown in this figure. This figure shows the observations from the Spitzer Space Telescope, or the SST. These infrared images a region of star formation, the remnant of an exploded star, and a region where an old star is losing its outer shell. Show just a few of the observations made and transmitted back to Earth from the SST. Since our eyes are not sensitive to infrared rays, we don't perceive colors from them. The colors in these images have been selected by astronomers to highlight details like the composition or temperature in these regions. In April 1990, a great leap forward in astronomy was made with the launch of the Hubble Space Telescope, or HST. With an aperture of 2.4 meters, this is the largest telescope put into space so far. Its aperture was limited by the size of the payload bay in the space shuttle that served as its launch vehicle. It was named for Edwin Hubble, the astronomer who discovered the expansion of the universe in the 1920s. With the Hubble, astronomers have obtained some of the most detailed images of astronomical objects from the solar system outward to the most distant galaxies. Among its many great achievements is the Hubble Ultra-Deep Field, an image of a small region of the sky observed for almost 100 hours. It contains views of about 10,000 galaxies, some of which formed when the universe was just a few % of its current age. Alright, thank you for listening. I hope you learned something. Stay safe, everyone. Our assessment will be posted later. Thank you. Have a great day. Bye-bye.